Hello and welcome to the Maths 2 component of the online BSc program on data science and programming. In this video, we are going to talk about computing integrals and areas. The idea here is that we have now reached a place where we know how to compute an integral, which is to say a definite integral, and we know that a definite integral represents area, namely it represents what is colloquially called area under the curve. Of course, the curve could be below the x-axis, so we have to interpret that suitably. So, we know how to do that, and now we will use this to compute areas. Okay, so let's recall first what we have done so far in the series on integrals. So, we had of course defined the definite integral from a to b of a function f, which was that we took Riemann sums and then we took the limit as the Riemann sums. The underlying partitions on the Riemann sums became finer and finer, and we hope that this limit exists, and that was called the integral. And the integral was representing, as I said, the area under the curve. But this was a rather difficult approach to take to compute the integral, because computing limits is hard. That is what we have understood from the videos on limits. So, we always try to bypass computing limits by either making good hypothesis on our functions or by proving theorems that allow us to compute them in different ways. So, Newton's theorem was what we studied in the previous video, and Newton's theorem allowed us to compute these integrals via the indefinite integral, or in other words the antiderivative. So, it linked up derivation and integration. So, let us go through the statement. The integral, which is denoted as integral f x dx of the function f defined on the domain D, is a function capital F defined on the domain D such that capital F prime x is little f of x for all x in D. So, this integral f x dx is equal to capital F of x. That's what the statement is saying. And what is the defining property of capital F of x? When you differentiate capital F of x, you get little f of x. Right. So, it is the antiderivative, which we prefer calling the integral. Now, I am saying the antiderivative because, or the integral, because any two antiderivatives differ only by a constant. So, we know that up to a constant it will be the same function. Now, Newton's theorem said if f is, it had two parts, but I am stating the part that we really need in order to compute integrals. If f is continuous on the domain D, which includes the interval a comma b. So, now all the action is taking place on this interval a comma b. So, as you must have observed in the video so far, the domain D is just a placeholder. So, if f is continuous on the domain D, which includes the interval a comma b, and capital F is the integral of little f, then the integral from a to b of f can be computed by, so this integral is capital F of b minus capital F of a. So, this was one part of Newton's theorem, and this gave us a handle on how to compute integrals. Namely, you find the indefinite integral or the antiderivative of your function little f, and then evaluate it at b and a and take the difference of the two. So, this was the method. We saw a few examples in the previous video. So, the upshot is that if one knows the integral of a continuous function, by integral of course we mean the indefinite integral, then one can use it to compute the area between the graph of the function and an interval on the x-axis. This is the upshot of what we have done. Okay, so let us now study some basic properties of integrals. These are on the lines of properties for derivatives, and the proofs are basically the same as the proofs that we had for the follow from the properties for the derivative. So, I would strongly suggest that you try to prove them yourself, except for the last one, which I will do here. So, integral of c times f of x dx is c times integral of f of x dx. So, the constants, so c here is supposed to be a constant, which is a real number. So, that comes out of the integral. If you take a sum of functions and integrate that, then that is the same as taking the individual integrals and then adding them. Same for the difference. And then finally, we have something called integration by parts. So, this is a very important and useful idea, and the proof is actually quite simple. So, the theorem is, or the statement is, integral of f times g prime x dx is f times g of x minus integral of f prime g of x dx. Now, let us quickly give a proof of this. So, let us start from f times g of x and ask what is its derivative. So, what is d dx of f g of x? Now, we know by the product rule from derivatives that this is exactly f prime x g x plus g prime x f x, which if we write in terms of products of functions, we could have written as f prime g of x plus g prime f of x. Yeah, this is the same thing, right? This is how we define product of functions. Well, since the derivative of f times g is the function on the right, that means the integral of the function on the right is f times g, right. So, therefore, integral of f prime g plus g prime f of x dx is f g of x, and I think at this point you probably see what is coming next. Well, this is a sum. By the second property right here, we can split this sum. So, we can write this integral as integral of f prime g of x plus integral of g prime f of x, and I have forgotten my dx. So, f prime g dx plus g prime f of x dx, this is f g of x, and now when you move f prime g to the other side, you get exactly what you want. So, therefore, integral of g prime f of x dx is f g of x minus integral of f prime g of x dx. Yeah, this is exactly the statement that we have. So, this statement is called integration by parts, and this is a very useful although it is an easy trick, it is a very useful trick in practice to compute integrals, and we will do an example as we go ahead. Okay. So, those were the properties of some basic properties of indefinite integrals. Now, let us talk about definite integrals, which is really what we want to compute. So, the first few properties will follow from the properties of the indefinite integrals. So, if you take a constant times f, then you can move the constant out of the definite integral. You can do this either from first principles or from Newton's theorem, which will allow you to write both sides as in terms of capital F and c times capital F. Okay. Then the sum of functions, if you take the definite integral, that is the sum of the definite integrals, and the same thing for the if you subtract g from f, then and take the integral from a to b. Instead, you could first take the integral of f and subtract out the integral of g, both from a to b. Okay. Now, here is something a bit which you might find strange, which is if you integrate from b to a f of x dx, then you get minus of integral a to b f of x dx. Now, there is two ways of interpreting this. One is to interpret b to a as going backwards in the interval. So, when you do your when you do your Riemann sum, when we did delta xi, those things would be negative. So, would be negative lengths, and then your Riemann sums become negative, well, not negative, but they become minus of the usual Riemann sum that you would get, and hence you pick up this minus sign. So, that is from the definition perspective. The other is you could call this itself a definition. Okay. So, whichever way you prefer, the statement seems very natural. So, if you integrate from b to a of f of x dx, that is the same as minus of integral a to b f of x dx. Okay. The right hand side we know, and it makes perfect sense. The left hand side, as I said, you can either define it this way, or you can change your definition of the definite integral to include not just intervals, but sets which start somewhere and end somewhere, where the starting and ending point need not be the starting point need not be less than the ending point, it could be larger also. Okay. Either way, so this is a fact that you will find useful. For any c in R, so c is some real number, if you integrate a to b f of x dx, then you could integrate from a to c and then integrate from c to b and add them up. Okay. So, if c is in the middle, if c is somewhere in the middle of a and b, this seems like a perfectly natural statement. But if c is not in the middle, then you have to interpret this statement in the light of the previous statement here. So, if c is less than a, for example, then this is essentially saying that you will when you take the sum on the right, you will subtract out c to a, but then you will also add a to c when you add the second one, right. So, if c is less than a or c is bigger than b, you have to interpret this suitably in terms of what we have above. Okay. And final property on this slide. So, if f of x is greater than or equal to g of x for all but finitely many points on the interval a comma b, in fact, we can even relax finitely many, but then we would have to become a bit more technical. So, if for finitely many points, all but finitely many points, if f x is larger than or equal to g of x, then the integral from a to b of f x is also larger than the integral of a to b g x dx. This again seems a very natural property from the perspective of Riemann sums and from the perspective that the integral computes areas. So, one upshot of this maybe I should mention. So, if f of x is equal to g of x for all but finitely many points, then from here we would also get that f of x, integral f of x is equal to integral g of x. And the main take home from there is that the function need not be continuous. See, we have applied Newton's theorem and so on in many places that we saw that we could get nice ways of handling the integral was under the hypothesis that f is continuous. So, what this is saying is that even if f is not continuous at a few points, that is still okay. You can treat it as if it is continuous at those points and compute the integral in the same way. So, this is a useful statement in that sense. One further consequence of this statement is that if f of x is greater than or equal to 0, so if g of x is 0, then the integral from a to b f of x dx is also greater than or equal to 0. This is something that we find natural, because in that case the integral actually computes the area under the curve. That is where what our starting point for integrals was. Fine. So, let us do a couple of examples to set our ideas. So, here is the integral from 1 to 3 of x squared minus 4x plus 2 dx. So, I can break this up as integral 1 to 3 x squared dx minus 4 times integral 1 to 3 x dx plus 2 times integral 1 to 3 1 dx, right. And then I can compute this because I know for each of these how to get the antiderivative. So, for the first one, the antiderivative is x cube by 3. So, the integral of x square is x cube by 3, and we want to evaluate it from 1 to 3. Then we have x squared by 2, again limits from 1 to 3, and then x from 1 to 3 multiplied by the 2 outside. And now we substitute. So, the first term gives us 1/3 times 3 cube minus 1 cube. The second term gives us 4 times, I can take my half out. So, 4 by 2 times 3 squared minus 1 squared, and the third term gives us 2 times 3 minus 1. And now, if we compute this, this is going to be 1/3 times 27 minus 1, so that is 26. So, 26 by 3 minus 2 times 9 minus 1, so 2 times 8, which is 16, and plus 2 times 2, which is 4. So, this is whatever it is, 26 by 3 minus 12, right, and you can probably do better. So, this is minus 10 by 3 and that is our answer. Okay. So, I hope it is clear how to compute these integrals, and how do I know each of these, how did I get from step 2 to step 3? That is because by observation I know that x to the power n, the integral is x to the power n plus 1 by n plus 1. So, if you do not remember these basic integrals, you could either try to sort of work out from the derivatives how to do them, or just look up tables if you find it confusing. Okay, let us look at the second example. So, in the second example, we have integral x squared sin x dx from minus 2 to 2, and there is certainly no obvious way of calculating this integral based on whatever we have done so far, because for this we need to know either the integral of x squared sin x. Well, we can compute this, but it is a little bit of a trick, and you can do it using what is called integration by parts, which we will see in a few slides. And other than that, we really do not know. So, what is the antiderivative of x squared times sin x? Yeah, to get it directly would require some imagination, some playing around with the terms, etc. So, how do we do this integral? Well, the trick here is to observe what happens, to observe the limits of integration and what kind of function x squared sin x is. So, if we plot x squared sin x, how does it look like? Well, so if f of x is x squared sin x, this is really the main point. If you look at f of minus x, this is minus x squared sin of minus x, which we, so minus of x squared is x squared and sin of minus x is minus sin x. So, this gives us minus x squared sin of x, which is minus f of x. Well, what does that mean? That means, for example, if you take f of 1, or rather f of minus 1, that is minus f of 1. If you take f of minus 2, that is minus f of 2. And so, if you think of what is happening here, if x squared sin x looks something like this, then minus x squared sin x looks something like this. So, there is a symmetry about this. Only thing is the symmetry is on the negative side. Okay. So, if you have this to be minus 2 and this is 2, what it is basically saying is, if you split up this integral into two parts, minus 2 to 0 x squared times sin of x dx plus integral 0 to 2 x squared sin of x dx, we know we can split it like this. That is one of the rules that we saw. Well, what does the first part compute? The first part computes this area, but with a negative sign. And what does the second part compute? The second part computes this, but with a positive sign. And well, clearly these areas are the same, but the first one, which is this one, comes with a minus sign. So, in other words, we are saying that this term is equal to minus integral 0 to 2 x squared sin of x dx, and then when you add it to the same thing, of course, you get 0. So, the answer to this integral is 0, and here the trick is to observe that your function has this form, f of minus x is minus f of x. So, this always this applies to all functions which satisfy f of minus x is minus f of x, and where your integral has limits which are symmetric about 0. Okay. So, let us do a couple of other properties. So, integration of piecewise defined functions. So, if a function is defined on certain pieces, so if f is defined piecewise on subintervals of a comma b, then its definite integral from a to b can be computed by computing the definite integrals on each subinterval and adding them up. So, let us do an example. So, suppose you have f of x which is defined as x on 0 to 1, and it is defined as 3 minus x from 1 to 2. What is integral 0 to 2 f of x dx? So, to compute this, we will break it up into each part on which it is defined. So, it is 0 to 1 f of x dx plus 1 to 2 f of x dx but 0 to 1 this is exactly x, and 1 to 2 this is 3 minus x. Now, notice that this function is actually not continuous at the point 1, because the left limit is 1 whereas the right limit is 2. So, this function is not continuous at the point 1, but that is okay. If it is not continuous at a few points, we can still do our integrals, no problem. Okay, so we just do them as we usually do. So, this is x squared by 2 from 0 to 1 plus excuse me. So, 3 minus x, the integral will be 3x minus x squared by 2 from 1 to 2, and now I will evaluate this rather fast. So, this is half plus 3 times 2 minus 1 plus minus 1 half 4 minus 1. Okay. So, this is half plus 3 minus 3 by 2. So, half minus 3 by 2 is minus 1, and then 3 minus 1 is 2. So, this is what you should get. So, the answer is 2. So, I hope the idea of what is written here is clear, that if you integrate piecewise defined functions, you have to integrate them on each subinterval they are defined on, and then add up to get the total integral. Okay. Integration by parts. So, we saw this already for the indefinite integral. Now, let us apply this for definite integrals. So, if you apply it to definite integrals, what you get is, if you integrate f g prime of x from a to b, then that is the same as f g evaluated from a to b, which means you take f g at b minus f times g at a, and then you subtract out integral a to b f prime g of x dx. Okay, here is an interesting example which you may actually see later on, maybe in your statistics course. So, integral 0 to infinity 3x e to the power minus 3x. So, I am deliberately taking infinity here to make you comfortable with the idea of integrating till infinity. So, to do this, what we have to do is we have to integrate 0 to b and then take the limit as b tends to infinity. So, let us see what this is. So, this is 3x times e to the power minus 3x dx. So, now let us interpret this in terms of our integration by parts. So, the key question here is what is f and what is g, and the idea is that you should choose f to be such that f prime becomes nice. So, this last integral is something easy to compute. So, if you have integral, so if I choose f of x to be x and I choose g of x, so that means I am choosing g prime of x to be 3 times e to the power minus 3x. Well, then what is g of x? This is minus of e to the power minus 3x. So, if you differentiate g, you get minus of minus 3 times e to the power minus 3x. So, that gives us 3 times e to the power minus 3x. So, indeed this function minus e to the power minus 3x is the integral of 3 times e to the power minus 3x, and so I know f, I know g. F prime is particularly nice because when I differentiate x I get 1. So, I am in a position to apply this formula. So, let us do that. So, if you do that, we get excuse me. So, first let us consider what is f times g. So, f times g is x times minus x times e to the power minus 3x, and we evaluate this from a to b. So, here we are at 0 to b, that is the first part, this part, that is what I have written down. So, that is this part here, and then the second part we still have to integrate. So, this is 0 to b f prime, which we just noted was 1, multiplied by g. So, what is g? E to the power, or rather minus e to the power minus 3x dx. Okay. So, the first term is going to give us minus b times e to the power minus 3 times b, and what happens to the second term? So, in the second term we have minus integral of minus e to the power minus 3 x, but we know how to integrate e to the power minus 3 x, we did it right here. So, the integral of minus e to the power minus 3 x is going to be e to the power minus 3 x divided by 3, right. So, if you differentiate this function e to the power minus 3 x by 3, what are you going to get? You are going to get minus 3 times e to the power minus 3 x divided by 3. So, you will get minus e to the power minus 3 x, which is exactly what we have here. And now, I want to evaluate this from 0 to b. So, the net result is that minus b times e to the power minus 3b minus e to the power minus 3b by 3. I should put this in the bracket, and then minus e to the power minus 3 times 0. So, that is e to the power 0, which is 1. So, this is minus 1/3, and so I get minus 1 minus b times e to the power minus 3b minus 1/3 times e to the power minus 3b, and then plus 1/3. So, I get a constant plus 1/3. Okay, now, what happens to limit, because we want to allow b to tend to infinity. So, to get the final result, we need to allow b to tend to infinity for this function here, minus b e to the power minus 3b minus 1/3 e to the power minus 3b and plus 1/3. So, the last thing is a constant. So, that remains as it is, and for the first two terms, note that we have an e to the power minus b, and for the second term it directly goes to 0. For the first term, well, we have it multiplied by b, but now if you remember our video on how fast do functions grow and so on, the exponential decay occurs much, the exponential beats the polynomial. This is what was there. So, e to the power minus 3b is going to go to 0 much faster than b is going to increase. So, in other words, this function here is also going to go to 0. So, that is something that we have to know. So, this is going to go to 0. So, this tends to 0. So, why? Because the exponential beats the polynomial. This is what you have to keep in mind. So, the first term goes to 0, the second term goes to 0, and so what we get is 1/3. So, you can see that by doing integration by parts, we could solve this problem. Now, of course, there are other ways of solving this problem. For example, you could be clever and try to guess an integral for this function. In fact, we have essentially computed that by integration by parts. So, maybe you could have guessed that function, and that is another way. But slowly it starts becoming difficult to always be clever. Instead, you can try and apply these nice results and keep simplifying the problem, and then hopefully you can reduce it always to integrals that you know how to compute. That is the idea of these techniques. Okay, so the last thing we are going to see is something called substitution. So, what this is saying is that if you have integral a to b f of g of x times g prime x dx, then that is the same as the integral g of a to g of b f of u du. So, in other words, this u is playing the role of g of x. Now, although I have written it from left to right, so it seems as if the term on the left is simplified by the term on the right. Often in practice, what you will do is you will go from right to left. So, you will take u and you will substitute u to be g of x. And here is an example. So, let us look at integral from 0 to a of root of a squared minus u squared du. So, what is the substitution here? So, the substitution here is, so you put u to be a times sine of x, right, and then what are the limits? The limits are, so limits for u are from 0 to a. So that means the limits for, so the limits are, so the limit for x is going to be 0 to pi over 2, right, because at pi over 2 it takes the value a. So now utilizing what we have upstairs, we will rewrite this as integral from 0 to pi over 2, right. So what this is saying essentially is that g of 0 is 0, g of so what is g? G is this function a times sine of x, and then what is g of 0? It's a times sine of 0, which is 0. What is g of pi over 2? It's a times sine of pi over 2. We know sine of pi over 2 is 1. So this is a. So a times 1 is a. So this is in the form that we have on the right, and so we will apply the form on the left. We will equate it to whatever is on the left, and so what we will get is 0 to pi over 2 f of. So what is f here? F is this function root a squared minus u squared. So root a squared minus g of x squared. But what is g of x squared? So a times sine of x the whole squared, which is a times sine squared of x. Okay. So I will just complete this. So f of x is root of a squared minus x squared, and so f of sorry, my bad, I should write f of u maybe. So f of u is a squared minus root of a squared minus u squared, and so f of g of x is root of a squared minus g of x the whole squared, which is root of a squared minus a squared sine squared x. Okay, so I hope I have completely explained this if you are seeing this for the first time. Okay, and now I have to do more, right? I have to multiply this by g prime of x. So I have to multiply this by a times cosine of x, and then I have dx, right. So that is how I have got from the right term to the left term. So this first term here, root of a squared minus u squared du, was the term on the right, and I have applied g of x to be a times sine of x, and I have got the term on the left. So there is a trick here, as you can see, namely I am using a very particular substitution. That is the trick here. Okay, now of course, in order to use this, in order for this to be useful, we need to be able to compute this integral after changing it. So let us see if we can do that. So you have integral a squared minus a squared sine squared x. So you can take a common. So you have a outside, then root of 1 minus sine squared x. But we know some trigonometric formulae. Sine squared x plus cosine squared x is 1. So 1 minus sine squared x is cosine squared x. So root of cosine squared x is cosine of x. So all in all, this square root gives us a times cosine x. We already have an a times cosine x here, and then we get a dx. So I have 0 to pi by 2 a squared times cosine squared x dx. Now I have to compute, so I can take a squared out. So get 0 to pi over 2 cosine squared x dx, and now I have to compute the integral of cosine squared x. But again, this is something that you might remember we did in the video on we used a formula for cosine squared x in the video on limits, and the same kind of idea is going to work here. So what should I do here? So what I will do here is I will express cosine squared x in terms of cosine of 2x. So this is integral 0 to pi over 2 1 plus cosine of 2x divided by 2 dx, and now this is an integral that I really know how to compute. So I will do this last thing rather fast. So the first integral is going to give me just x over 2, or maybe I can pull the 2 out, the half out. So this is a squared by 2 x plus and now I want the integral of cosine of 2x. Well, I know what that is. Integral of cosine is sine, so I get sine of 2x, but now since I have 2x, I have to divide by 2. So this is what the integral is, and now I have to compute this from 0 to pi over 2. Okay, so if you work that out, this is going to be a squared by 2 for the lower limit, which is 0. None of the terms contribute, since x evaluated at 0 is 0, sine of 2x evaluated at 0 is 0. So, the only term that will contribute is pi by 2. So, you get a squared by 2 pi over 2 plus sine of 2 times pi over 2. So, that is sine of pi divided by 2, but we know sine of pi is 0. So, what we get is pi a squared divided by 4. So, finally, let us come back to computing areas. So, this is just a small example, which is the circle. So, we saw two ways of computing the area of the circle. One was by the method of Archimedes, the very beautiful way of taking regular polygons and then filling it up and then allowing the sides, number of sides to increase, first from inside, then from outside, and then bounding it on both sides, and that gave us what the area was. I did not do that computation, but I mentioned this and it is something that those of you who are more interested can try to work out on your own. The other way I did it was I cut the circle or the disc rather into smaller what are called annuli, meaning you take small strips, circular strips, and then we unfolded them, then we sort of bent them down, so that it was almost like a rectangle, except that the top was curved, and then we put them all together, and then we took the limit. This was sort of an idea that we used to give the intuition for integration, and then we observed that in the limit this becomes like a triangle, and we computed what the area was. Okay. So, both of those methods were very nice, and only thing is that they involved computing some limits, which we kind of did a little bit of a hand wave for. So, now I am going to use integrals to compute this area. So, what I will do is I will draw this line here. So, let us think of this as the x axis, let us think of this as the y axis. Note that there was no line given to me as such, and all I need is the radius. So, suppose the radius here is so radius is a. So, this is the circle of radius a. Then what is the area of this circle? That is what we are trying to find out. Well, now I can interpret the top. So, I will compute the area of the top part, okay, or maybe even the part in the first quadrant. So, I will compute the area of this part. Okay. How do I do that? Well, I think of this part of the circle, this arc here. I can try to think of this as a function. So, this is a function from where to where? This is a function defined on the interval 0 through a. And what is that function? Well, for this we need to write down the parametric equation of the circle. So, remember that the circle satisfies that x squared plus y squared is a squared. That's all the points which are on the circle. So, all those x comma y which satisfy this is exactly what defines the circle. So, those ones which are in the first quadrant mean that x is positive and y is positive, and so I can write y as, rewriting this, I can write y as root of a squared minus x squared. That is a familiar expression. And so, I can look at the function f of x is root of a squared minus x squared, right, and I can ask what is the integral 0 through a of f of x dx. What is that? Well, that is exactly this thing in the green portion that we have done here. Why? Because that is the area under the curve, where the curve is the graph of this function. But what is the graph? The graph is exactly this blue arc that I have drawn. Okay. So, this green portion is exactly going to be computed by integrating f of x dx, where f is root a squared minus x squared. How do I do that? Well, let us go back. This is exactly what I did over here. So, I computed root a squared minus u squared du from 0 to a was pi a squared by 4. So, this is pi a squared by 4. but now the area of the circle is 4 times this area, right. So, it is 4 times pi times a squared by 4, where remember that a is the radius. So, this gives us pi times a squared. So, if you think of your radius as r instead of a, you would have gotten pi r squared, the formula that we know, and now we have a complete proof of this. So, I hope this explains to you how to one sort of way of how we are going to compute areas using integrals. So, in short, integrals are a very powerful tool for many things, and you are going to come across them in statistics in particular, but they are also useful in more basic geometric operations, in particular in computing areas. And I will strongly urge that you try to compute, for example, other things like the area of the ellipse or the area under the hyperbola and so on. Thank you.